Okay, so team challenge number 14 is a PCR question. Now PCR is a fairly simple concept, but to actually get down into the nitty-gritty of the various orientations and numbers and how the whole thing fits together causes some problems for people. So let's go through this pretty carefully. So first of all, we have a gene. It happens to be an RNase gene from a cyanobacterium. And we're given the gene sequence. In the first part of the problem, it asks you to suggest a pair of primers to amplify the sequence of the gene by PCR. So when you're trying to get primers that will amplify this gene, you have to remember that there are two strands. Only one of them is shown here. It's the coding strand. And there is implied another strand, which is the template strand. So the forward primer is exactly like the sequence at the beginning of the coding strand, but it's actually going to bind to the other strand, which is the template strand. So a typical forward primer would look like the very beginning of that gene. So it's A, T, G, T, C, T, G, A, T, G, C, C, and so on. And I would make it a roughly 24 bases long. Remember that it's going to bind to the other strand and extend that way. Now the reverse primer is actually going to bind to this piece of DNA that's shown here, and so it's got to be the reverse complement of the very end of this sequence. So the end is a stop codon, TGA, and we are going to have a strand that starts at that A with a complementary base. So it's 5' end here is a T, C, A. So it is binding to the very end of the gene and working inwards. So it would have a sequence like TCA, ATG, AAT, and so on, until you get to around 24 bases. I don't think this is the concept that most people are struggling with. Most people are struggling with, how many primers and how many DNTPs do we need to make up the gene? So let's look at this gene. It says in the top of the problem the position in the genome, that it's position 2261556 to 2262335. This is the first nucleotide, and this one is the last nucleotide. This is part of a larger genome. This genome is about 6 million base pairs long, and then it's these positions that make up this gene. So in order to figure out how long the amplicon is, or the part the gene is, the part we're amplifying, I have to subtract the first number from the last number. Okay, which gives me something, it would be 779, but this one is actually part of the sequence, and what I really want to do is to take this and subtract the base that comes right before in order to get the full length of the gene. So I have to add one or subtract a different number, which gives us a value of 780 base pairs. Now what does that actually mean, 780 base pairs? It means this: the amplicon is a double-stranded. So every time there's a base here, there's a complementary base here, and that makes a base pair. Okay? And what it is that we have a primer at the beginning of each. So let's imagine orientation here. It's 5', 3', 5', 3'. At the 5' end of each strand is a primer, and in this case it says that the primers are 22 bases long. Okay. The whole thing is 780 base pairs, which means there's 780 bases in this strand and 780 bases in this strand. Okay, but in terms of where they came from, we say that 780 minus 22 came from free nucleotides, so 758. bases came from free nucleotides, or DNTPs, whereas 22 on each strand came from the primer. And so we have 758 bases times 2 being the number of DNTPs it takes to make one amplicon. So we have a total of 780 bases plus 780 bases. Okay, so one is at 1,560 bases total, but 44 of them came in the form of primers, and the others came from DNTPs that were incorporated as the DNA polymerase filled out each of these strands. Okay, that number, 1,560 DNTPs per amplicon, another way of putting that would be 1,516 picomoles of DNTPs per picomole amplicon. Okay? So this is going to lead nicely into the next part of the question, which is about what you have in your reaction, and really what this is about is determining what is limiting the reaction. What's the limiting reagent in this reaction? It says that we have 10 microliters, okay, which is equal to 1 times 10 to the minus 5 liters. And the solution has 5 picomoles total of each primer and 8.8 millimolar DNTPs. So we have 8 times 10 to the minus 4 moles per liter of DNTPs. Okay, that's 0.8 millimolar. So if I multiply this out, I get 8 times 10 to the minus 9 moles of DNTPs in the solution, which is 8 nanomoles if you like, but I'm going to go right to picomoles. This is 8 nanomoles, or 8,000 picomoles of DNTPs. That's what I have in my tube. That's the most DNTPs I could possibly incorporate. So now the question becomes, I have 5 picomoles of primer pairs, and each amplicon needs a forward and a reverse primer, a pair. So the maximum number of amplicons I could make would be 5 picomoles, using up all the primers that are in the solution. If I did that, if I made 5 picomoles of amplicon, I would need a certain number of DNTPs. I would need 15, 16 picomoles DNTP per picomole that I made. Okay? So I can really easily figure out how many DNTPs it would take to make those 5 picomoles of primers into amplicon. And the number that we get there is 7,580 picomoles of DNTPs. Okay? To use up all the primers, I would need 7,580 picomoles of DNTPs. I have 8,000 picomoles of DNTP, so I have more than enough. So what this tells me right away is that this is primer limited, not DNTP limited, and therefore my maximum yield is simply 5 picomoles of amplicon. If I didn't have 7,580, it would be DNTP limited, and I would have to figure out how many picomoles of amplicon I would make, knowing how many picomoles of DNTP are in every picomole of amplicon. So I would have to divide the number of picomoles of DNTPs that I had by the number per picomole of amplicon to figure out how many picomoles of amplicon I could make. So in this question, it turns out to be primer limited with a yield of 5 picomoles of amplicon. Now the final step here is to figure out how many amino acids are in this protein encoded by this gene and what the molecular weight is. So we had 780 base pairs in the gene, and we know that there are 3 bases to encode each amino acid. So this gives us, or per codon if you like, this gives us 260 codons. Alright? The only thing we have to bear in mind here is that one of those codons is the last one, the stop codon, and that doesn't actually add an amino acid, it just terminates the translation. So we end up with 259 amino acids in the protein, and each amino acid is 110 grams per mole. So our molecular weight, if I multiply this out, would be 28,600 grams per mole of that protein, which in biochemical speak we would call a 26.8 kilodalton. But 28,600 grams per mole for that protein RNase.